random variable, a random variable capital X. Random variable capital X takes the values. Take the values is -2, -1, 0 and 1. 0 and 1 with probabilities is 1 by 8, 1 by 8, 1 by 4 and 1 by 2 respectively. Find and draw. Find and draw the probability distribution and density function. Probability distribution and density function. What he is asking that he is giving the events in random variable, and he is also mentioning what are the probabilities is having those events. According to this data, he is asking you can able to find the distribution and density function. Already we know that what is the given elements and its corresponding probability we are calling the density function. That's why I am writing the solution for this one is what are the probabilities we are having but corresponding elements we are forming in a table. This can be representing the probability density function. The elements is capital X and its corresponding probability is P of X. P of X, the elements are -2, -1, 0 and 1. 0 and 1. And I am writing the negative values, but you don't confuse. But the probability distribution and the probability is not having the negative values. Here I am not writing the probability values. It's only the element values. Element values. The element values are -2, -1, 0 and 1. The corresponding probabilities is 1 by 8, 1 by 8 and here 1 by 8 and 1 by 4 and 1 by 2. 1 by 2. This one is probability density function. Probability density function. Now we need to find the probability distribution. Probability distribution. Before going to probability distribution, we can plot this density function. The probability density function, here I am plotting that. X-axis is random variable and the y-axis its density function is fx of x. Fx of x. What are the points we are having? -2, -1, 0 and 1. Then I am giving that it's a -2 notation. This one is a -2 and -1, 0 and 1. Here the given random variable is discrete or continuous. According to given data, each and every value is having the unique quantities. That means discrete quantities. Discrete quantities. That's why the random variable is discrete random variable. For a discrete random variable, the graphical representation of a density function is impulse. That's why I am representing the quantities and I am giving the values. 1 by 8 is less value. That's why I am giving this 1 by 8. And next 1 by 4. And next is 1 by 2. 1 by 2. Now I am plotting that impulse response. At -2, the quantity is 1 by 8. 1 by 8. And at -1 is also the quantity is 1 by 8. 1 by 8. At 0 quantity, the value is 1 by 4. So 1 by 4. At 1, the quantity is 1 by 2. This is a graphical representation for a probability density function. Coming to the next one. What's the next one? Probability distribution. Probability distribution. You need to find the distribution values at -2, -1 and 0 and 1. -2, -1, 0 and 1. Here first I am finding that the distribution at -2, the effects of -2 is equal to, directly I am writing that Why? Already know that the formula is fx of x is equal to the probability of capital X less than or equal to small x. According to this property, I am directly simplifying this probability distribution function. The distribution at -2 value is probability of capital X less than or equal to -2. Here, according to this one, only we are having that the probability at -2. That's why I am writing that the probability capital X is equal to -2. At -2, the quantity is 1 by 8. 1 by 8. Then you can finding the next quantity is fx of -1. The distribution at -1. You are writing that the quantity is probability of capital X less than or equal to -1. -1. Here, what is the less quantities of -1? In negative numbers, the higher values is very less. Higher values is very less. According to this one, I am writing here the probability at x is equal to -2 plus the probability at x is equal to -1. -1. Here we are having that is the two values. Those two values are 1 by 8 and 1 by 8 plus 1 by 8. Totally the 2 by 8, the value is 1 by 4. 1 by 4. Coming to the next one, what is the third one? The fx at 0. Fx at 0, the quantity is probability of capital X less than or equal to 0. Less than or equal to 0. Here equal to 0 and less values of 0. The combinations are the probability at x is equal to -2 plus probability at x is equal to -1 plus at probability at x is equal to 0. Is equal to 0. Now we can substitute in the values. The first two quantities already are finding the quantity is 1 by 4 and third quantity is already is given is 1 by 4. That's why I am substituting these all values. So 1 by 4 plus 1 by 4. The quantity is 2 by 4. Value is 1 by 2. Coming to the last distribution, that one is fx at 1. Fx at 1 is equal to the probability of capital X less than or equal to 1. Here totally having the 4 pairs. The 4 pairs are at x is equal to -2, at x is equal to -1, plus at x is equal to 0, plus at x is equal to 1. Already the three quantities are we are finding. The three quantities values is a 1 by 2. That's why I'm finally writing is a 1 by 2. And the last quantity at 1 is 1 by 2. The total value is 1. Total value is 1. What are the values we are obtaining? The first quantity is 1 by 8, and second quantity is 1 by 4, and third quantity is 1 by 2, and fourth quantity is 1. The values are increasing is 1 by 8 and 1 by 4 and 1 by 2 and 1. Now you can plot this all values in a coordinate system. Now I am plotting this all values. What are the values we are having? Fx of -2, the quantity is 1 by 8. Fx of -1, the quantity is 1 by 4. Fx of 0, the quantity is 1 by 2. Fx of 1, the quantity is 1. These values we are able to representing on graph. X-axis I am taking the random variable capital X, and y-axis I am able to taking the probability distribution function is fx of x. Fx of x. The elements are -2, -1, 0 and 1. Here the random variable is discrete. Random variable is discrete. That's why the distribution function is stair step form. Stair step form. First of all, you can represent the quantity at -2 and -1 and 0 and 1. Here you can also give the indications on vertical axis. This quantity is 1 by 8 and this quantity is 1 by 4. This value is 1 by 2. This value is 1. The first quantity we are representing in step form at -2, the quantity is 1 by 8. 1 by 8. We are making the step function, that's why I am taking the constant magnitude up to next value. At -1, its magnitude is 1 by 4. 1 by 4. I am extending the magnitude up to 1 by 4. I am making the constant magnitude up to next value. Next value is 0. At 0 quantity, its magnitude is 1 by 2. 1 by 2. I am extending the magnitude up to 1 by 2. It is having the constant magnitude up to next value 1. At 1, the magnitude is 1. That's why I am extending its values up to 1. This step is making the constant values up to infinite. This one is a graphical representation for probability distribution function. A continuous random variable capital X. Continuous random variable capital X has the distribution function. Here, how to identify which is a continuous? Already we know that the definition of a continuous random variable. The continuous random variable is having infinite values in finite interval. Here the finite interval we are representing in comparison operations like 0 less than or equal to x less than or equal to 10. This is the representation for continuous random variable. Continuous random variable. Here we are simplifying the given data. What is the given data? He is given that it's a probability distribution function. Probability distribution function. He is asking, you can able to finding that the probability density function. How you can finding that the density function? We are having the relation. What is the relation we are having? The relation between density and distribution function is the density function is always the derivation of its distribution is a d by dx of fx of x. Fx of x. Based on this relation, we can able to finding the density function. Already is given that the distribution function. We are not multiplying the 4, it is a power of 4. So 4. Now we can find that value from this distribution. Now I am able to find this density function from the distribution. Just I am making the derivation on this distribution function. The first one is fx of x. The fx of x is equal to at 0 value. At 0 value, the quantities never change. This value is also having the 0. The condition is if x is less than or equal to 0. Less than or equal to 0. Next, coming to the second one. What is the second one? It is having the k into 1 minus x whole power 4. Whole power 4 if the interval is 1 to x less than or equal to 3. Here you are making that derivation. You are making the derivation of this entire function. This entire function we are making the derivation. What is the function we are having? The derivation of is a d by dx of k into 1 minus x whole power 4. Whole power 4. Here k is a constant. K is a constant. X is a variable. We are able to apply the derivation on variables only. That's why I am writing the k, the derivation of d by dx of is a 1 minus x whole power 4. Whole power 4. One out to have the derivation, how you can writing that? The derivation of x power n. N into x power n minus 1. That means the property is d by dx of x power n is equal to n into x power n minus 1. N into x power n minus 1. According to that property, I am simplifying that one. Here I am rewriting this entire function is k into the derivation of this power term, I am writing the 4 into 1 minus x power 3. Power 3. I am also derivating this x with respect to x. The value is minus 1. Minus 1. Now you can writing this value is 4 into k 1 minus x power 3 power 3. The value is minus. Value is minus. This one is the density in the interval of 1 to 3. 1 to 3. We are finding the values. So k into z by dx of 1 minus x power 4. The whole power 4. We are writing that. That's why we are making that the power is multiplying and its power quantities we are minimizing. And also you are able to apply the derivation on individual term is x. The derivation of minus x, the value is minus 1. That's why I am multiplying this entire quantity. The final value is minus 4k into 1 minus x whole cube. X whole cube. That one is a quantity. Now you can find in the third value. Here I am representing that the minus 4k 1 minus x whole cube, the interval of 1 less than x less than or equal to 3. That one is the second value. Coming to the third one. What is the third one? The third one is a 1. The third one is 1. When the value of x is more than 3. More than 3. But here we are applying the derivation on a constant numbers. Array constants. Array constant, the value is 0. The value is 0. That's why we got 0 value when I were to applying the derivation on 1 in the interval of x value is greater than 3. X value is greater than 3. Here I am writing that x value is greater than 3. Now quantity is 0. These are all the values. Now you need to find the value of k. The value of k. How to find the value of k? According to the property of density function, we are finding the k value. All of you clear that? Up to now, what we can do that? We are taking that the fundamental relation between density and distribution function. Already the distribution function is mentioning in this problem. Then you have to make the derivation for this each and every quantity in a particular intervals. Finally, we are representing the corresponding quantities in this function. This function we are calling that the probability density function. Now we can able to finding the k value. K value. How to finding the k value? Here we are taking that the second one. The second function value we are consider for finding the k value. We are having that the fundamental property. The fundamental property in density function. When the interval is lying is x1 less than x less than or equal to x2, we are writing the integral of x1 x2 of x of x into dx. X of x into dx. Here, but we are taking that the second property. The second property is the valid condition. The integral of minus infinite to plus infinite f x of x into dx is equal to 1. We are taking that the second property. By using that one, we can able to find the k value. Now I am simplifying this equation according to the second property. The second property is integral minus infinite to plus infinite f x of x into dx is equal to 1. Dx is equal to 1. Here we are having the density function interval is 1 to 3. 1 to 3. The function is minus 4k, the 1 minus x whole cube is into whole cube into dx is equal to 1. Now can you able to apply the integration on this function. Minus 4k is a constant term. That's why I am writing the outside of interval minus 4k interval of minus 4k. I am writing the minus 4k outside of integration. The integration is 1 to 3. 1 to 3. The term is 1 minus x whole cube into dx is equal to 1. Here I am applying the integration. The integration of x power n is equal to x power n plus 1 divided by n plus 1. N plus 1. According to this property, I am able to simplify this function, the integration of 1 minus x whole cube. I am rewriting this function in terms of x power n plus 1 divided by n plus 1. Then we are able to differentiate this quantity and we are multiplying this entire value. That one is a property we are having in integration and differentiation. That's why I am writing some minus 4k minus 4k integration. Here I am applying the integration on this function. That one is minus 1 minus x 3 plus 1 divided by 3 plus 1 into minus 1 into minus 1. The limits are 1 to 3 is equal to 1. 1 to 3 is equal to 1. Here you can be able to apply minus 1 and minus 1 totally plus. Here you can simplify this one. I am taking this as a 4k. Minus minus both are cancelled. We have got is a 4k. 4k into 1 minus x whole power 4 divided by 4, and its handle limits is 1 to 3 is equal to 1. Here denominator 4 and numerator 4 both are cancelled, and top and bottom both 4s are cancelled. Remaining elements are k into 1 minus x whole power 4. The values are 1 to 3. 1 to 3 we are having the values. 1 to 3 is equal to 1. Here I am moving the k value. K is a constant, that's why I am moving k to right hand side. Then we can substitute in the limits. Where x is there, we can substitute in the higher limit is 3, and minus lower limits we are substituting that. Here we are substituting the higher limit minus lower limit. That's why I am writing k is I am moving to right hand side. Here k is multiplying, when I am moving k value in right hand side, it is divisible. 1 minus 3 whole power 4 minus 1 minus minus 1 whole power 4 is equal to 1 divided by k. 1 divided by k. Here 1 minus 3. 1 minus 3 means what is the quantity? Minus 2 whole power 4. Minus 2 whole power 4. Here minus 1 plus 1 both are cancelled, quantity is 0, is 1 by k. 1 by k. Here minus power 4, that's why the minus can be cancelled, it can be changed into positive. Then the 2 power 4, the quantity is 16. 16 is equal to 1 by k. 1 by k. From this, k value is equal to 16. So 1 by 16. K value is 1 by 16. Now you can representing the k value in density function. Just where k value is there, you can just put in that the k value is 1 by 16. Here I am replacing the density function with the value of k. The first value is 0. The interval of x is less than or equal to 0. In second one, I am here, the what is the k value is there, so 1 by 16 I am substituting. That's why the 4 and 16 is cancelling. Remaining value is minus 1 by 4, 1 minus x whole cube. The interval is 1 less than x less than or equal to 3. If the quantity of density is 0, the interval is x value is more than 3. More than 3. This one is a finalized density function for a given problem. Remaining thing we are discussing in next class. Students, today class we are going to discussing about is one of the problem is relating to probability distribution and density function. Before going to that one, what is given that? The given topic is relating to the continuous random variable or a discrete random variable. What is given? In a given problem, he is completely and clearly mentioning that the spin wheel is a pair spin wheel is marked from 0 to 12. 0 to 12. He is asking you can be able to find the probability density and distribution functions. Then you can plot that. What is the density function, graphical representation, and distribution function, graphical representation. First of all, you can see that how the spin wheel is there. The graphical representation of a spin wheel is like this. This one is a spin wheel. The spin wheel, the center, it is marked from 0. Here I am giving the indication is 0 to 12. 0, 1, 2, 3, 4, so 5 and 6, 7, 8, 9, 10, 11 and 12. According to given data, he is given the spin wheel, it is marked from 0 to 12. 0 to 12. What he is asking? You need to find the probability density function and the probability distribution function for this spin wheel outcomes. Here, each and every value can representing the outcome of spin wheel. This entire values execution is like a continuous. It's like a continuous. That's why this one is one of the best example is belongs to continuous random variable. Today class we can simplifying the probability density function. Now here I am writing that the solution of this one. What do we need to find? Here we are finding that the probability density function. The probability density function. Here each and every event. First of all I am writing that the sample space. The sample space, already you know that the indication is S. Here what are the outcomes we are having? Those outcomes are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These all are the outcomes. Each outcome must have that the unique representation. At a time only one values we are obtaining, but according to the given data we need to plot what is the probability density function. For finding the probability density function you need to find what is the probability for each and every event execution. Here I am finding the probability of 0 occurrence and 1 occurrence and 2 occurrence. In these values is only having the unique appearance. How many possible outcomes is available in this experiment? Totally having 0 to 12. 0 to 12. That's why we are having that the 13 possible outcomes. 13 possible outcomes. These are the 13 possible outcomes. These 13 possible outcomes are is a sample space. Here we need to find the probability for 0 occurrence and 1 occurrence and 2 occurrence. Now I am writing the probability of 0. The probability of 0 occurrence is equal to the desired outcome. Occurrence is only 1 chance. Remaining the total possible outcomes is 13. Next I am writing for getting the 1 value, the probability is 1 by 13. Why? Because Only we are having that one event. Only one event. That's why I'm writing is 1 by 13. For getting the 2, the probability is 1 by 13. 1 by 13. Similarly, you can write in the all elements individual probabilities for occurrence of their events. That's why I'm writing is the probability of 4, the probability of 3 is equal to 1 by 13, and probability of 4 is equal to 1 by 13, and probability of 5 is equal to 1 by 13, and probability of 6 is equal to 1 by 13. Similarly, you can write in remaining elements is the probability of 7 is equal to 1 by 13, and the probability of 8 is equal to 1 by 13, and the probability of 9 is equal to 1 by 13, and the probability of 10 is equal to 1 by 13, and probability at 11 is equal to 1 by 13, and probability of 12 is equal to 1 by 13. 1 by 13. Here, each and every element is having that unique probability. Unique probability. That means at 0 execution, the probability is 1 by 13. For 2 and 1 and 2, all elements is having the same probability. Why? Because it is having that only unique occurrence. Unique occurrence. That's why you can writing that each and every element in this pinwheel we are writing its probabilities is 1 by 13. 1 by 13. Now we will draw that. What is the graphical representation for a probability density function? Now I am plotting that the graphical representation for a probability density function. Here I am taking that random variable x on horizontal axis and the density function. Already we know that what is the probabilities we are obtaining from a given data, those probabilities and the elements combination we are calling the density function representation for a corresponding experiment. Based on that one, here I am writing that the graphical representation of a density function. Okay, density function. On x-axis I am representing the elements. The 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm extending this line. 11 and 12. So it's x. Now you can identify what are the points we are having based on their probabilities. What are the values we are having? The first value is 1 by 13 at 0. At 0 quantity, the probability is 1 by 13. Here you can give that indications. Here the magnitude is, I am representing at 1 by 13. The magnitude quantity is 1 by 13. At 0 point, the value is 1 by 13. At 1, the magnitude is 1 by 13. According to given data, the random variable is a discrete or continuous. Discrete or continuous. We are having a small description about discrete random variable and continuous random variable. When the random variable is discrete, the graphical representation for a density function is impulse. If the distribution function for a discrete random variable, it is a step form. Here we are consider the random variable is a continuous nature. Continuous nature. For a continuous random variable, the density function is continuous and distribution function is also continuous. That's why I am representing all magnitudes. What are the quantities we are obtaining from the elements? Here draw that is a constant. That is a constant means a continuous representation of a graph. Here at quantity 0, we are having the 1 by 13. At 1 is a 1 by 13. At 2, 1 by 13. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At each and every point, we are obtaining the constant probability value. Constant probability value. That's why according to the analysis of continuous random variable, the graphical representation of probability density function, I am representing the continuous nature. This one is a graphical representation for spin wheel probability density function. The PDF for spin wheel marked from 0 to 12. 0 to 12. Similarly, we are able to obtain the probability distribution function. Probability distribution function. How to obtain the probability distribution function? Already we know that. The basic formula regarding to probability distribution function. The formula is the probability of capital X less than or equal to small x. This one is the capital fx of x. Capital fx of x. This one is a fundamental definition for a probability distribution function. The fx of x is equal to probability of capital X less than or equal to small x. According to this property, we are obtaining each and every distribution function value. That's why we can writing the values of probability distribution function. Here I am writing that at 0. That means the capital X less than or equal to 0. We are writing the capital fx of 0 is equal to the probability of capital X less than or equal to 0. The quantity is, what is the quantity we are having? So 1 by 13. 1 by 13. Similarly, you can writing the remaining quantities at fx of 1 is equal to 2 by 13. 2 by 13. At fx of 2, the value is 3 by 13. 3 by 13. And fx of 3, we are writing the quantity is 4 by 13. 4 by 13. Similarly, the remaining quantities we are writing here. The fx of 4 is equal to 5 by 13. And fx of 5 is equal to 6 by 13. And fx of 6 is equal to 7 by 13. Fx of 7 is equal to 8 by 13. And fx of 8 is equal to 9 by 13. And fx of 9 is equal to 10 by 13. And fx of 10 is equal to 11 by 13. And fx of 11 is equal to 12 by 13. And fx of 12 is equal to 13 by 13. The value is 1. Value is 1. Finally, what we are obtaining from a given data, we are obtaining the each and every probability for each and every event. Those are representing probability density function. From these density values, we are obtaining the distribution by using the fundamental formula. This one is the fundamental formula. By using this formula, we are obtaining the remaining values. Already we know that how to expanding this equation based on their range. That's why I am writing that remaining all values. Now we are representing the graphical representation for a probability distribution. Probability distribution. How we are representing the probability distribution? Here I am giving that x-axis and y-axis. X-axis and y-axis. According to given data, the nature of random variable is continuous. The nature of random variable is continuous. When the random variable is continuous, the distribution function graphical representation is also continuous. It's also continuous. That's why I'm representing the all quantities on this coordinate system. At x-axis, I'm representing origin is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. This one is a random variable x. Random variable x. And in y direction, I am representing the quantities. What are the quantities we are having? Those quantities are 1 by 13, 2 by 13. Here I am giving the notation is 1 by 13, 2 by 13, 3 by 13, 4 by 13 and 5 by 13, 6 by 13, 7 by 13, 8 by 13, 9 by 13, 10 by 13, and 11 by 13. We have marked each and every value up to 1. Up to 1. Here we can representing each and every quantity. At 0 quantity, the probability distribution quantity value is 1 by 13. I can indicating the number is dot. And coming to the distribution at 1, the 1 value is 2 by 13. At 2 by 13, I have to give the indication is the dot notation. At 2 value, the distribution is 3 by 13. 3 by 13. At 3 value is 4 by 13. At 4 value is a 5 by 13. At 5 value, it is a 6 by 13. At 6 value, it is a 7 by 13. At 7 value, it is a 8 by 13. At 8 value, it is a 9 by 13. At 9 value, it is a 10 by 13. We are marked this all values up to 1. Up to 1. These all points we are joining in continuous orientation. Continuous orientation. Why we are joining this all in continuous? When the random variable axis continuous, the graphical representation of a probability distribution function is also continuous. That's why we are representing the probability distribution function in graphical orientation in continuous. Finally, what we are discussing, we are taking the spin wheel. In that spin wheel, we are finding the individual probabilities of each and every event execution. These execution probabilities we are calling the probability density function. From this density values, we are obtaining the distribution values by using this relation. After that, the density values, we are plotting the graphical representation of density function, and then what are the values we are having for a distribution, we are representing these all values in a graphical orientation for a probability distribution function. This one is a complete solution for this spin wheel. It's marked from 0 to 12, its density function and its distribution function. Good morning, students. Today class we are going to discussing about the problems on the probability density function. Good morning, students. Today class we are going to discussing about some of the problems is relating to probability density functions. Here he is given the one problem. In this particular problem, he is particularly asking that a continuous random variable x has the density function is fx of x is equal to k divided by 1 plus x squared. The value can be lying from minus infinite to plus infinite. What is asking that is to find the k value and distribution function. Here I am simplifying this one. First of all, I am writing the given data. The given data is fx of x is equal to k divided by 1 plus x square. It is lying from some minus infinite to plus infinite. Less than or equal to capital X, less than or equal to plus infinite. Is the density function. Here we need to find the k value. How to find the k value? Already we know that the fundamental property of density function. What is the fundamental property we are having? That there is a two main conditions for a valid density function. The first condition is small fx of x is greater than or equal to 0. And the second one is we are consider the limitations is a minus infinite to plus infinite. The density function is fx of x into dx is equal to 1. Is equal to 1. Any valid density function must satisfy these two conditions. Here I am taking that the second condition for obtaining the k value. Already we know that the density function is particularly mentioning in given data. That's why I'm writing the density function is k divided by 1 plus x square. Here I'm obtaining the k value. I'm taking the second condition of density function. What is the second condition? Integral minus infinite to plus infinite fx of x into dx is equal to 1. Now I am finding the k value. I am just substituting the where f of x is there. Just I am putting the fx of x value. Just here I am writing that is a minus infinite to plus infinite. K divided by 1 plus x square into dx is equal to 1. Equal to 1. In this equation, here the k value is a constant and x is a variable. X is a variable. That's why I'm simplifying this one. I'm writing that k is out of the integration. The integration is minus infinite to plus infinite, and remaining function is 1 divided by 1 plus x square into dx is equal to 1. Now I am moving this k value to right hand side. The remaining term is the minus infinite to plus infinite, minus infinite to plus infinite, the 1 divided by 1 plus x square into dx is equal to 1 divided by k. 1 divided by k. Here we are taking that the integration of 1 divided by 1 plus x square, the function is a tan inverse function. It is a tan inverse function. That's why I'm writing that the tan inverse of x, the limits are so minus infinite to plus infinite, minus infinite to plus infinite is equal to 1 divided by k. Is equal to 1 divided by k. Now I am substituting the higher limit and lower limit. Then I can find the k value. Here I am taking that the tan inverse plus infinite minus tan inverse minus infinite is equal to 1 by k. Is equal to 1 by k. According to this given data, we are easily finding that that's why it's a tan inverse of plus infinite, a tan inverse of minus infinite. When you getting that infinite value in a tan function, here the tan inverse of plus infinite, here minus infinite. The tan of minus x, we are writing that it's a minus tan x. Minus tan x. That's why here also we are simplifying this function is tan inverse infinite minus into some minus a plus. The tan inverse infinite is equal to 1 by k. 1 by k. Here how many functions we are having? 2 functions we are having that. That's why I'm writing the 2 functions is when you got this value, the tan inverse of infinite. In tan function, we got the value is infinite at 90 degrees. At 90 degrees. That's why we can make in the summation of these two quantities. The 90 is a 190 plus the another 90 is equal to 1 by k. Here 90 we are writing directly, 90 is indicating the degrees. That's I'm writing as pi by 2 plus pi by 2 is equal to 1 by k. From this we are writing as a pi. Pi is equal to 1 by k. 1 by k. From this one I am writing the k value is 1 divided by pi. 1 divided by pi. Now we are finding the k value, then we can easily finding the distribution function. What is the relation between density and distribution function? The relation is, already we know that the distribution is integration of the density function. Integration of the density function. That one is, I am writing here, the density function already is given that, just I am writing the distribution is fx of x is equal to integral minus infinite to plus infinite, minus infinite to plus infinite. The k values already we are obtaining that the value is 1 divided by pi, 1 divided by pi whole divided by 1 plus x square into dx, this function. Here just you can see that what is the integration term is there. The integration term we can replace its equivalent value. What I can do that only I am consider except this 1 by pi, what are the terms is available in this integration, I am treating this. The integration of 1 divided by 1 plus x square, we are writing that it is a tan inverse of x. It is a tan inverse of x. Now I am writing that this 1 by pi is a constant. 1 by pi is a constant, and the remaining term I am replacing with its equivalent value is tan inverse x. Tan inverse x. The value is varying from minus infinite to plus infinite. Minus infinite to plus infinite. That's why I'm indicating the limits is a minus infinite to less than or equal to capital X, less than or equal to plus infinite. Is a interval. Except this interval limitation, we got this remaining values are zeros. Here the distribution function is only this fx of x is equal to 1 by pi tan inverse of x, where limit is varying from minus infinite to plus infinite. Without this interval, the quantity is 0. Finally, what we are obtaining that we are obtaining the k value and the distribution function from a density function. We know the fundamental properties, just we are taking that where we can apply that. You can simply obtaining the final value of distribution function. Coming to the next one. Can you stop this? Coming to the next problem. In this problem is asking the find the constant, the b value is greater than 0 for the density function is fx of x is equal to e power 3x divided by 4. It is and the limits are 0 to b. 0 to b. Except these limitations, the value is 0. But what is asking that it is a valid density function. He is saying that find the value of b when the density function is a valid. Here you can make in the solution for this one. First of all, what is given that the given density function is fx of x is equal to e power 3x divided by 4. Divided by 4. It is lying between 0 less than or equal to x less than or equal to small b. Except this limits, the value is 0. The value is 0. But in this problem is particularly mentioning that the density function is a valid density. Valid density function. Already we know that the valid density function must satisfy the basic two properties in a density function. Here I am taking that the validity conditions of a density function. The second property is integral the minus infinite to plus infinite fx of x into dx is equal to 1. Dx is equal to 1. By using this property, I can find that value of small b. Value of small b. Here what is given that generally we are writing the limits is a minus infinite and plus infinite. But he is mentioning that limitation ranges is 0 and small b. 0 and small b. Now I am replacing these limits. So 0 and b. And here the density function is e power 3x divided by 4 into dx is equal to 1. Now we are applying the integration on exponential term. When not applying the integration on exponential term, we are getting the exponential term. After that, what is the term is having the power in exponential. We can make in the differentiation on this particular term, then you can writing in denominator. Now I'm applying the integration on this exponential term. I'm getting the exponential value e power 3x. Already the constant value is 4. I'm just writing the 4 in denominator. The remaining is, I'm also applying the differentiation on 3x. 3x value is 3. Why? Because it's a one time. And the remaining you can substitute in the limits is 0 and b is equal to 1. Is equal to 1. Now you can separate the constant value is 1 by 12. Remaining the value is e power 3x. Limitations are 0 to small b. 0 to small b is equal to 1. Is equal to 1. Now I am substituting these limits on this function. So it's a 1 divided by 12. The first higher limit is e power. I am substituting the higher limit is small b in this exponential term. So e power 3b. 3b minus e power 3 into 0. The value is e power 0 is equal to 1. Is equal to 1. Now I am moving this 12 value to right hand side. Then this equation can be changing to e power 3b minus e power 0. E power 0 quantity, we are writing that it is a 1. 1 is equal to 12. Now I am moving this minus 1 to right hand side. Then it can be adding to 12. 3b is equal to 13. 3b is equal to 13. From this value, I am writing the 3b. 3b is equal to, here I am moving this exponential value to right hand side. It can be changing to logarithm. So log of E13. E13 and b is equal to 1 by 3 log E13. We can find this value by using the scientific calculator. We are obtaining the value of b is 0.854. 854. What we can do in this problem, just we are taking that the density function from a given data. Then we are applying that the essential condition of density function. That one is integral minus infinite to plus infinite is fx of x into dx is equal to 1. Here just we are replacing that what is the density function is available in a fundamental condition, we are replacing. After that we are applying the integration on this density function. Then we are substituting the limitation values. From these values we are simplifying this entire equation, we are obtaining the b value.